Hello, everyone, and welcome to our presentation. I am Dr. Joby Hilliker, and I'm Associate Professor at Westchester University. If you're not familiar, Westchester University is about 20 miles outside of Philadelphia. I've been there for over 15 years, and I've been working with graduate student Ryan, and we are happy to present a topic called Ultra Short-Term Temperature Forecasting using an archive of Mesonet temperature and radiation observations. And I'm going to turn it over to Ryan, who will start out the presentation. Ryan, go ahead.
Thanks, Joby. As you mentioned, I'm Ryan Roberts. I'm a graduate student in the Earth and Space Sciences Department at Westchester University, and I'm also a full-time high school physics teacher at Conestoga High School in the Tredyffrin Easttown School District, which is another suburb of Philadelphia. Again, thank you for your interest in our project. So weather forecasts are pivotal to several industries, including but not limited to energy and transportation. For energy sectors, transportation is the primary weather parameter in load forecasting, particularly during the summer months when temperature is the highest. The establishment of ASOS is crucial to evaluating aviation safety and logistics. Many, but not all, of the more than 900 ASOS stations spread across the US are positioned at airports and generally report observations at hourly intervals. With increasing implementation of regional meso networks, such as the Delaware Environmental Observational System, the DEOS, the predictive ability of parameters such as temperature can be refined to smaller timescales. For the DEOS, observations of temperature are recorded every 5 minutes. With Mesonets such as the DEOS, meteorologists are able to investigate methods of improving ultra-short-term forecasting techniques. To that end, persistence is a well-known forecasting technique for the ultra-short-term timescale, which is here defined as less than or equal to 30 minutes in the future. However, forecasting accuracy can be increased by including previous data, known as persistence climatology, and including surrounding observational data through an observation-based system like the DEOS. One advantage the DEOS has over ASOS is the recording of solar radiation data. To that end, the goal of this study was assessing the value of incorporating surrounding observations and the radiation data for ultra short-term temperature forecasts using the DEOS. Temperature and radiation observations were obtained for the one-year period of December 30th, 2018 to December 30th, 2019. Of the available stations, the station at Wilmington, Delaware was selected for the test station due to its proximity to surrounding stations, several of which are upstream. The average distance between Wilmington test station and the 12 surrounding stations used in this study was 15 kilometers. And with that, I will throw it back over to Dr. Hilliker.
Very good. Thank you so much, Ryan. All right, in terms of the project statistical design, we had over 100,000 observations. As Ryan said, this was used for the full year of 2019, every 5 minutes. And we tested 3 different regression approaches. You can see I defined them here in this table. The first is stepwise regression, where the AIC is used to choose which predictors would be most valuable in the forecast equation. Number 2, very similar. However, the root mean square error was used as the metric, as the cutoff. And then finally, we incorporated something called elastic net regression. Elastic net regression is useful if you don't want too many predictors in your model. As you probably know, if you have too many predictors in your statistical forecast equation, you run the risk of overfitting. Overfitting basically means the model does great in your developmental data set, but unfortunately not so well when you apply it to an independent data set. Now, just some terminology that you're going to see for the rest of the presentation. We constructed a couple of different models. The first one we call the OBS, the OBS-based TR. T stands for temperature, R stands for radiation. So more or less, this was the full model incorporating both temperature and radiation observations for not only our test site, but our 12 surrounding sites constructed as part of the DEOS. And then we also tested a slightly pared down version of the model. We call this just the OBS-T, and this one, as you might surmise, just solely uses temperature observations. So by looking at the obs-TR and also the accuracy of the obs-T, we are gauging the effectiveness of incorporating radiation observations in the system. Now, a quick summary of what we did with our data. So as you know, we had a lot of observations. Traditionally, you devote 3/4 of the observations to what you call the developmental data set. This data set is used to develop your statistical forecast equations. And then the remaining 1/4 of the observations are called the independent data set. And this is a data set used to generate the forecast using the equations you already constructed. By the way, we did normalize the data, and we also took 20 different random samples of our data set. All right, suffice it to say, we constructed a lot of equations and a lot of forecasts. We constructed equations for each of the different models. So the full model, the obs-TR, the slightly pared down version, the obs-T, and also persistence climatology. Persistence climatology is a model where you just use the most recent temperature observation at the test site. We also tested 4 different lead times between 5 and 30 minutes inclusive. We also tested for each hour of the day, and we also used each of the 3 regression approaches I showed you in that table a couple of minutes ago. Now, of course, a big question is, how do we gauge forecast accuracy? And we used a commonly used metric called the mean absolute error, the MAE, and we averaged the MAE over all 20 samples. All right, and now for the results. One portion of the results section revolves around what were the most powerful predictors. In other words, when you look at these statistical forecast equations, what was the composition of the predictors? And this is what this table reveals. Each row represents a lead time. Each column represents a candidate predictor, okay? And the percentage that you see there represents the percentage of equations that that particular predictor appeared in the full model, okay? Now, one thing that is clearly apparent is that for all the lead times, it is the most recent temperature observation at the test site, which is found in most, if not all, of the forecast equations. Not too much of a surprise, because that is, of course, persistence climatology. By the way, you get a little bit of insight if you include the previous temperature observation. One big takeaway message, though, from this research is right here. When you incorporate the most recent radiation observation at the test site and the previous radiation observation, those two appeared in most of the equations. And very interestingly is that if you look at the coefficients of these two particular predictors, the sign of the coefficients are reversed. So the suggestion is that you want the change in radiation to help you in terms of making a more accurate 5-minute temperature forecast. Now, this change in radiation is pretty valuable for a 5-minute and to a certain extent the 10-minute forecast. But once you get beyond the 10-minute forecast time, the stepwise regression did not want any radiation observations in the forecast equations. Conversely, though, what becomes more important for longer lead times is the inclusion of the most recent temperature observations at surrounding locations. And some of the more popular locations that the system chose were stations L, B, J, and E. And those stations were located more or less upstream of our test station. Okay, and now to the results. And this plot shows the accuracy of our various models as a function of the hour of the day. One thing I should mention is that the x-axis represents time, the hour of the day, and this is local time. And of course, in Delaware, we're talking about Eastern time. The y-axis represents the error, the mean absolute error. The higher the number, the greater the air. What I'm showing here, just for simplicity, is the air for the 5-minute forecast, and up here is the air for the 15-minute forecast. Now, one thing I want to get out of the way is that more or less the air was comparable for all the 3 different statistical approaches that we chose. This one, I'm showing the stepwise regression, and I want to draw your attention to the lines that represent the 5-minute forecast air. The red line is the full model. The blue line is the model that just uses temperature observations solely. And one thing that's pretty clear is that during the afternoon, that lead time, or that air, becomes less right around between 1 o'clock and 4 o'clock with the inclusion of radiation. And remember, in the table before, it is the inclusion of the change in radiation which furthers the accuracy over forecast beyond what just simply having the most recent temperature observation can offer you. By the way, this improvement in the full model averages about 6% during the daylight hours, maximized during the late afternoon to around 12%. This perhaps is not surprising because, remember, in a well-mixed atmosphere, particularly during the summer, you have a lot of turbulence, a lot of eddies, and a lot of parcels of slightly different temperature and dew point that move over the station, okay? Now, for the 15-minute lead time, a couple of things are different. One thing that's apparent is notice how the air is more or less the same for the full model and also the OBS-T. Now, this is consistent with the table I showed you a couple minutes ago, because remember, for the 15-minute lead time, there are no radiation predictors, more or less, that deem to be valuable for the 15-minute lead time. So the red line and the blue line are more or less the same. What is critical, though, is this second takeaway message from this research, and that is when you use an OBS-based system for forecasting temperature in the ultra short term, notice the improvement you get over just using persistence climatology, which is shown by the gray line. This increase in accuracy using an OBS-based system ranges from 11% at the 5-minute lead time to 17% once you get out to the 30-minute lead times. So in conclusion, for this narrow window of forecasting temperature for the ultra short-term lead times for the warm season for the afternoon hours, we feel that there are 2 major conclusions from this research. The first is that at the 5-minute lead time, you want to incorporate the change in radiation at your station for making temperature forecasts even more accurate beyond what PC can offer you, persistence climatology. And the second conclusion is valid for lead times beyond 5 minutes. So for lead times that go out to 10 minutes, 15 minutes, and 30 minutes, it is important that you incorporate the temperature at surrounding locations at your test site. And those test sites, you probably want those stations to be upstream, as Ryan said, anywhere from 5 to 10 to 15 kilometers from your test sites. So that's what we have. We thank you so much for your time these last 15 minutes and sharing what we have to offer with our research. Thank you so much, Ryan, for working with me. It's been a great collaboration this past year or so, and we'll be happy to answer any questions during the chat session in January. Thank you so much.